All right, welcome back. So now that we've seen the few different linear programming forms, what I want to do is I want to go back and forth and be able to take from one form to another. Specifically, let's just stick with the standard form 1. So we're going to go from inequality form to the standard form. All right, and I'll show you the few tricks we need to do that, and vice versa. Let's go from standard form 1 back to inequality form, and there's a few other tricks that we need. Okay, so let's get started. So the first thing we're going to do is we're going to assume we're starting here, and we need to go to the standard form. So what are the few things that we see here? Well, first of all, x in the inequality form could be negative. The variables could be negative. So that's a problem with in standard form. I need my variables to be non-negative. All right. And the other issue is that we have inequality constraints, and we need those to be equality constraints. All right. So let's choose one. Let's start with the inequality constraints. Let's turn them to equality. Okay. So one thing we can do is if I say AX, I know AX is less than B. All right. But if I add a new variable, all right, let's say Z. Okay. We'll call this the slack variable. All right. A vector of Z's. So that's just slack variables. Z is equal to Z1 dot 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 Zn, and of course Zi have to be greater than 0. Okay, so if I add a positive value, depending on what remember these are M equations, okay, then I can get equality. I think you could agree with that. Now the Z's might be different, right, depending on the situation, the problem, but if I've got slop, then if I add a positive constant, I will be able, depending on what that value, how far away from B it is, this Zi, I can add that value to get an equality. Okay? So what I've done now is I've now appended, so now my new x, and I'll call it x hat, my new variables, so my new variables, okay, are now the original x, okay, and these new variables z. All right, so there, that was pretty easy. We just added a slack variable to each equation, or a slack variable vector to the ax. So that allows us to have an equality constraint, but we're still stuck with some non-negativity problems. Now the nice thing is Z is fixed as a non-negative, so I don't have to worry about those, but I still have to deal with X. Okay, so I'm going to do a little trick, and I'm going to say, and let me go, so that is my equality. Let's worry about non-negativity. Non-negativity, and let's say I have the new variable of x hat. Okay, so one thing is I'm going to do a trick. I'm going to say x is equal to or I should say xi, some variable ri minus si. Okay, so where Ri and Si are greater than or equal to 0. So the nice thing is that I can produce a negative value with two non-negative variables. Okay, so remember, this is positive or non-zero, greater than or equal to 0. This is greater than or equal to 0, but this may be less than 0 with this combination. All right, so that's it. I just replace the variable x with two new variables. So that means that, and that means that my my x hat is equal to r, the vector r, and the vector s, and the vector z. All right? So this is our new vector. Now let's play with it a little bit, and let's be able to turn this form into this form. And I'm going to rewrite it as C hat transpose X hat, and A hat, or I can leave it as, yeah, A hat X hat is equal to B hat, so that we don't confuse between the original C, A, and B. And of course, X hat is greater than or equal to 0. Now in this case, this is already taken care of. All right? If R X hat, every one of them, R, S, and Z, are all greater than 0, so that part is taken care of. Okay? So now, let's go ahead and put it into a more compact form. All right? So remember that C transpose X, but I've replaced X with R minus S, so that you get C transpose R minus C transpose S, giving you a new vector. So let me minimize. Giving you a new vector, which is minimize C minus C and 0 transpose times your new vector R, S, and Z. Okay? So this is your new C hat transpose. And of course, this is your X hat. So now we've taken care of the objective function. We now can move on to the constraints. All right? Now remember that we had A, X, plus Z is equal to B. So that's equality. That's great. But we have to get rid of X. So it's AR minus AS plus Z equals B, giving us A minus A identity, and then of course times R, S, and Z is equal to, keep confusing those, is equal to the vector B. And now we have, this is our new A hat. Of course, this is X hat. And this is actually, even though it's still B, it's also our new B hat. So in this case, B hat is equal to B. That hasn't changed. And that completes our conversion. We're back to C hat time transpose X hat subject to A hat X hat is equal to B or B hat. In this case, B and B hat are the same. And then, of course, the non-negativity constraint, A hat is greater than or equal to 0. So by definition, we've defined R, S, and Z to all be non-negative. So that's taken care of. We've cleaned up and removed X by the important equation X equals R minus S, and turned this problem from inequality form into equality, or to the standard form. Okay, so that was that's probably the trickier one of the two. Okay, now let's go ahead and see how we can go the other way. Okay, so let's move on and let's do standard form. Okay, to inequality form. Now this actually will be a little easier because we don't have to add slack variables. All right, so C transpose X, that because we're not going to add, you're going to see we're not going to add any more variables, so we don't have to change. In this case, let's still call it X hat. Let's redefine this as C hat transpose X hat, and A hat X hat is less than B hat. Okay, just so we don't confuse. But in this specific case, you'll see that C hat and X hat are the same as C and X. All right. The only difference is your A hat is going to look a little bit different, and so is your B. Okay. So I think that you would agree that let's get rid of the non-negativity constraint from the standard form. All right, and let's put it into inequality form. Well, if I multiply it by a negative, so I get negative I, and just to make it easier when we put it into the final form, I think you would agree identity times X is still X. So minus X is less than 0. So now we've got this less than or equal to, which is sort of what the form we want it to be. So that's about ready. So this is the non-negativity. Now the AX is equal to B as an equality. How do we change that to inequality? Well, I think that if I say AX is equal to B, I think you would agree that that's the same as AX is greater than B and AX is less than B, giving you two equations, AX is less than B and minus AX is less than minus B. That comes from the negative, that the AX is greater than B, and to flip the greater than to a less than, I just multiply by negative. All right? So I've turned this equality into two inequality forms, and that is the trick. Okay? So let me finalize this equation. So I get back to C transpose X, because my variable X has not changed, subject to, minimize, subject to, all right, now we have A times X minus A times X and minus identity from the non-negativity, and that's less than equal to B minus B and a vector of zeros. Be more specific. So now we have our new A hat. X is still X hat, and X are the same in this case, and my B hat has changed. All right, so that completes this. As you can see, this was a little bit easier because I didn't have to add slack variables or turn a variable that could be negative into forcing it to be variables that are only non-negative. Okay, so those are the tricks. Hopefully that made sense. Watch it again if that was too fast. And thank you. I'll see you next time.